Right, so I'm going to talk today about the Wolfram Compiler. So this is a new compiler project for the Wolfram language. It's a long-term project. We've been working on this for a while, but hopefully soon we'll be having some sort of releases, things that people can use. It's going to be a replacement for the old compile technology. It's a completely new implementation, and it's built in the Wolfram language. So let's just start off with a sample. So the new idea is you compile the basic level, you're compiling functions. So we're compiling functions, and we give type markup in a different way with this thing called typed. So we say, integer 64, and we get the answer when we invoke it. So the flow of processing of the compiler goes through a number of stages. So we generate an inert form of the Wolfram code. We transform this Wolfram code applying various transformations, macros, analyses that are convenient to do on the tree-structured Wolfram code. And then we generate an intermediate representation. We do type annotations, we expand function definitions, we do more transformations, optimizations. Then we generate instructions for a thing called LLVM. We optimize the LLVM code, we generate machine executables, and then we can start executing. Now, an alternative flow of the thing is that the first steps are all very similar, but then we go straight from this Wolfram intermediate code to some alternative executable mechanism, maybe C++ or JavaScript, so not using LLVM. Right. So, just a quick rundown. First step, we create this inert form of the Wolfram code. So this is, once we've got to this form of the Wolfram code, it's not going to, it's not going to execute, and we can do all sorts of useful things with it as a representation of a Wolfram expression. Next stage we do is we take that and we generate this intermediate representation. So again, I'm not going to give too many technical details of the compiler, but this is what's known as an SSA, a single static assignment representation of the Wolfram code. And it might not look like it, but this is actually has the form of a lambda expression, but that's technical detail. It's got type annotations, and we've got things like this that's calling into a library of runtime, a runtime library. So I've given talks at previous conferences about the compiler, and this is like the latest updates, moving hopefully soon to a release. So the biggest new feature that we have here is we have an entirely new representation of types and type inferencing mechanism. There's a new runtime. So now we're starting to do actual coding and program generation. We have some new parallelism features. We have machine code and assembler generation, more streamlined and optimized. We integrate nicely with LLVM optimization, and we have some integration with LLVM debugging mechanisms. So, we'll talk about the type system for a little bit, especially since type system is very mathy, and at least some of you here are interested in mathematics. Type system actually touches on a very interesting core part of mathematics that's really some of the things that are at the very core, the mathematics of mathematics. So it's very interesting. So some of the benefits that you get from a type system, so you can get verification of your program. You can know that the program won't, you'll have confidence that it won't reach a point and then run out of ways to progress. It won't sort of halt. There are ways that it can halt, but many of the ways that might halt can be detected at an early stage, and when you uncover problems at an early stage, they're quicker to fix. The particular type system that we have has a sort of what's known as a polymorphic way of working with it, and that's useful because it means a little bit of code can go a long way. So it's efficient. Type system is a way of doing reasoning about the code. You get knowledge and ability to do reasoning, and that's pretty useful because then you can start to do optimizations that are specific to particular types. So for example, the simple operations like, say, addition, adding numbers together. If you have floating point operations, IEEE floating point operations, machine number floats, then addition is not associative. So you have to preserve the order. If you want to get reproducible answers, you can't reorder the way that you do the additions. And you might want to do that because if you're adding lots of numbers together, you might want to make some sort of binary tree to reduce the number of operations. On the other hand, if you're doing operations over integers, it's quite valid to go and reorder the operations. You might find a faster way of doing it. So that's benefit. Another benefit of a type system is you can create code that is reaching much closer to the machine hardware. If you know more about it, you can target exotic hardware, or even if you don't have exotic hardware, you can reach closer to the actual code. So there's a number of benefits. So the type framework that we've put together supports what's known as static typing. We run a typing pass at code processing time. We have an inferencing mechanism, and that's very useful. So in older typed languages, you had to put type annotations everywhere in your code, and using a type inferencing algorithm, we minimize quite significantly the number of annotations that are needed. As I said before, it supports a parametric polymorphism mechanism. A little bit of code goes a long way. Another interesting thing about the framework we've built is it's actually independent of the compiler. You don't have, it's not part of the compiler, it's independent. So the compiler uses it, but other things could use it as well. So now, some of the things that it doesn't support, so we don't have the big thing that we don't support is any notion of subtyping. So there's no object-oriented typing, there's no template mechanism. And actually the parametric polymorphism is a more modern alternative to object-oriented programming. Was very popular 10, 20 years ago, but it's now not so fashionable. And we don't support things like C++ templates, which is, for me, with my little brain, is a good thing, actually. So, right. So, some of the details. It's based on it's a Hindley-Milner system with modifications, with extensions. And I can talk about what those are. So it has its origins in a typed lambda calculus with various sort of extensions. And that's, you might say, well, this is Wolfram language. How can you use knowledge of lambda calculus to, because Wolfram language isn't a strict lambda thing. And that's why the translation into this, intermediate form is useful, because that is a form of lambda calculus. So it fits with another Wolfram project that's going on. I think there's going to be a talk I'm for doing that's closer to the mathematics of type theory that's using types for theorem proving. Now, as I understand it, theorem proving is they're both aspects of type working with type systems, but in a sense, theorem proving is you start with the type, and then you have to find a program that has that type, whereas what we're doing is much easier. We start with the program, and then we infer the type if it has one, or we say, no, it doesn't, it's not well typed, in which case we reject it. And as I said before, it fits with sort of mathematical logic, which goes right to the core of mathematics. So, in addition to these sorts of things, we have to support the Wolfram language. So it's not going to be very useful if it's so restrictive. And a couple of these things are kind of important. So we have to support functions that take any number of arguments, that take multiple arguments, more than one argument, or more than a fixed number of arguments, and maybe even an arbitrary number of arguments. I mean, we have to do that. And in a stricter, typesys or stricter languages, they very often support only one argument, and they use a form of currying. So if you have, like plus of, a comma b, what really that is that's like plus of a is returning a function which adds to another, another argument. But we can't do that. It would be too restrictive. And even more complicated is the actual type depends upon what the arguments are. And we need a way of encoding this into the type system. So you might imagine, say, like the part function. So we could say part of an integer, that's going to make a reduction in the sort of depth of the expression. And then you could say, well, there's two of them. That's going to lead to two orders of reduction in the depth. But here's another part where we give the list structure. So this actually doesn't lead to a reduction of 2 stages, it's just the reduction of 1. So the actual type of, these are all different versions of the part function, and they have different types because of the output type is, it's not just a factor of the number of arguments. And we have to take care of this. So we have a number of, these are sort of type expressions that we can support in our system. So we can have an atomic type, integer, Boolean. We support function types. This is the way we write function types. So we have a list. This is the input, and the output is Boolean. Now, let's get more exotic. So here we have a type. This is called a handle, and this depends upon another type. So this is like a handle. We use, these names are sort of arbitrary, but this particular type, we use it to hold something that would be like a reference or a pointer to something that we need to. And so this handle is quite general, but it needs one argument. And that could be an integer, it could be a function, it could be something else. So we have these polymorphic types. So here's a polymorphic type. So this is a type that has, this is like a function in type space. So this is the argument is v, and this is any type, and the actual thing is going to be a function that takes that type and returns the same thing. So for example, this would be a good implementation of a type, not implementation, a type for an identity function. Now, these polymorphic types become more useful when you put predicates onto them. So for example, here, I'm putting a predicate. I'm saying it's a variable, but this variable has to satisfy a property, and for these, it's a membership of a set. So we say there's a set called number, and this thing here has to be an element of the number set, and it's a function. So this would be suitable for, say, like some unary math function, like abs or you know, unary minus or something like that. And then the last thing we have is we have types that depend upon terms. So this is a composition. So we have, like, we call this a number array. This is how we represent packed arrays. But raw arrays are somewhat similar. And so the base sort of quantity that's in there is integer, and we have a 2. And so this is the number of indices. This would be a matrix. If it was 1, it would be a vector. If it was 3, it would be, you know, some sort of higher tensor. It's not really tensor in the physics sense, but... Well, here's another example. This is where we're specifying the length of something. So this would be a type that represents a vector of integers of length 2. And this might be a matrix of integers. Well, it could be booleans, or it could be functions. A matrix of something, and it has 2 rows and 5 columns. So with these, it's quite an expressive language. So we can start to write type signatures. So here, for example, this is a function. This would be suitable for an append type function working on this vector thing. So this is a vector of something. We haven't said what that something is. It could be integers or booleans or reals or functions or whatever, and of a length. And we haven't said what its length is, but the output is going to be a vector of the same base, but now we've incremented the length. So this would be an append function. Or here, I've written a type signature for a matrix multiply. So we have a matrix. It has like rows and columns, and another matrix, rows and columns. So it's a bit like pattern matching this. These variables are a little bit like pattern variables, but we say the number of columns has to match the number of rows. Or am I getting that? No, that sounds right. And the output is going to be a matrix of this type here. So it's quite succinct language, and we're able to represent, quite useful properties in such a way.
Is everything strings to avoid evaluation, or is there some other?
Types, the names of types are strings.
To avoid evaluation? Or?
That's what we've done. Okay. Right. Now, let's look a little bit at some operation of this inferencing system. So I have to restart my kernel. Got to keep an eye on the time. Now, so this is, I'm not using the compiler, I'm just using the type system. So I'm going to initialize a type environment. This is like a built-in type environment. It has a bunch of types and knowledge and things. And I'm going to create a type inferencing state for working with a lambda, with a sort of mini language. And I'm going to do some inferencing. So what I have here is I have a lambda function. This is a little bit like function. And it takes an argument, and it returns that same argument. And I'm going to apply it to an integer, a constant 1. And the output's going to be 1. So this is the essence of typed lambda calculus. You have terms, so this is a term. You have abstractions, functions, that's the lambda function, and then you have application. And when you look at a book on lambda calculus, this is where it starts. So we can do inferencing on this, or we can take the same thing and apply it to a Boolean, and we get Boolean. So that's all good. Here's another. So we also have added a mechanism for adding knowledge of functions. So here I'm applying something that's a variable, and it looks this up in a mechanism, and it's applying a thing called identity, and it's applying to the to true, and the answer comes back, that's going to be a Boolean. And this is the mechanism that we have. So I'm looking up this is all done sort of internally in the inferencing mechanism, but I'm looking in the type environment, I'm looking up the identity function, and this is the type. So it's using one of these type for alls. And we can go lots deeper. I mean, don't really have to go in for this, but we've developed this Lambda mini language, and we use this for development and testing and understanding of the type framework. And we can do this independently of the compiler, which we found pretty useful. Now, let's restart. Hopefully everything's going to restart again. So now I'm switching back, and I'm actually going to show a little bit how this type framework is used in keeping an eye on the time. And so now I'm going to generate some Wolfram intermediate representation, but I'm sort of turning down, I'm sort of halting the conversion process at a very, very early stage. And so what we see here, we've got type, we know what the types of the arguments are, they're integers, but there's a plus, it's u. We don't know what type plus has, and we don't know what type the output is. And the same for times, and we don't know what the result of this is going to be. So now we're going to run an inferencing. We're going to do inferencing on this, and now everything we've determined all of the types that we might want to know. So we know that the function is taking two integer 64s and returning an integer 64. We know that the plus that's here is the version of plus that works on two integers and returns an integer, and the same for times. So now we've added quite a lot of knowledge to the system. So a next stage would be to then go and look up implementations and maybe create them. They might be written polymorphically, so in which case they'd have to be instantiated, and we're going to look those up. So we run a function resolution pass, and it then goes and has created, so we've now got calls. So this is now specialized the plus to a specific plus that takes particular arguments, so it adds sort of name mangling system. Maybe we might use a C++, someone might ask if we aren't using C++ name mangling, and probably we should accept. The names are so horrendous, it's quite useful being able to read the things. And then these, so now we've got these two functions. This is a call into the runtime library, which is called in a particular way, so we can track runtime errors in the arithmetic that might be necessary. We might want to track those. So this is now making more progress. We might also, I haven't shown this, we might decide to inline these function definitions or not. There's lots of strategies and such like. So, and I'll just note something about this inferencer is it's not just, this is what's kind of cool, it doesn't just go forwards, it sort of goes backwards and sideways, and if there's enough knowledge, it'll produce the answer, and if there isn't, it won't. So here, I'm creating a handle. This is like one of these reference things. And we know that the handle, we know that it's a handle, but we don't know what sort of handle it is. So we have a variable here. But notice I'm storing in the handle the argument, and I know what the argument is. It's an integer 64. So now, when I run the inferencer, it resolves all these unknown variables. It goes through this process, unifying things, finding substitutions, and it's able to sort of infer all the types. So without a lot of markup, it's able to produce the correct result. So we've been developing an ontology, a name of types etai.
So you started out with just this function which added two N64s, and then you said, unless I missed something, you just said convert stuff, and it decided that the output is going to be an N64. But of course, the sum of two N64s is not necessarily
we're working in the domain. The plus function that we have decided to use is one that takes, we're working in the domain of int64. That's what it does. It's an error if you don't. If you don't like that and you want to be able to go wider, then you should be using a different type which we'll be providing. But that's not. But if the output doesn't fit into an int64, you'll know that. Okay? I'd like to keep going, if that's okay. We can talk. We have an ontology of names of types that we've been working through. These are the sorts of names that we're coming up with. Of course, these names are completely arbitrary, but we choose common conventions, sort of, etc. Now, so this is the sort of thing that huge amounts of work goes into, and most people don't really, but it's super important to get this right. We need a library to provide common arithmetic and utility functions, and we need to really understand how they're working. We need them to be, this is totally eating your cake and having it, because we want them to be super fast and very understandable in how well they work. So this is a big development effort that we have to build this library. It's being implemented at a C++ template system. It's shared, another nice thing, it's shared between the compiler and the kernel, so we get, we only have to write one bit of code, which is useful, and things work in a common sort of way. We're using latest compiler technologies where we can track these errors and things in very efficient ways, and it would also be a standalone library. So if we had standalone compiled applications would work. Now, so the compiler and LLVM. We use LLVM as a backend. Stephen was showing this last night. So what is LLVM? So the first thing to remember about LLVM is it's not a VM. So, right, lots of people think, it's a VM like the Java VM or Python, whatever. It's not. LLVM is a compiler infrastructure. It's like GCC or some, other compilers. And it provides a large collection of compiler tools for working with different input languages and output targets. And what's really nice about it is it's written, actually I often think LLVM, if we were writing something like it, it would be the way that we would write it. It's written very nicely as a set of reusable components, and it's very well set up for extension. And this might contrast it with GCC, which is a very respectable compiler technology, but I think it's probably true that to do similar sorts of things to what we're doing here with GCC would be extremely hard. But actually, as I can attest, you can get to grips with LLVM and look at the source code and understand how it works. If you're interested in compilers, that is, it's quite, it's quite robust and easy to work with. So, it has this well-defined intermediate representation, which is kind of, isomorphic with the Wolfram intermediate representation, which is, GCC has a similar thing as well. LLVM is there's a lot of momentum, a lot of work behind it at the moment. It's the basis of the Clang C++ compiler, and it's backed by lots of companies, and it's an emerging, there's more and more support goes into LLVM. I think its origins at the University of Illinois, just down the road. There's lots of tools that work with LLVM, debuggers, transformers, profilers, etc. And it has all sorts of things that people do with it, like integration with GPUs. So, but I'm just going to stress, this is just a convenience. We're not specifically tied to LLVM, and I think we're starting to explore developing alternative backends. We might want to compile into C++ or compile into JavaScript. And then we probably would not be using LLVM. We'd just go from our intermediate representation. Right, fine. Now, generating LLVM, just generate it. Here's the output. It's actually kind of the same sort of thing. This is a string representation. There's a binary representation, which is called bitcode. Not Bitcoin, bitcode. Right, so how are we doing? Right, so LLVM provides a nice feature that's called awk-JIT. So awk stands for on-request compilation. And I've read the story that the developer of awk-JIT thought it would be really cool to write something called awk. So what can I write? So he started with the name, and then he thought of the project to fit it to. But it's turned into this great useful thing. The nice thing about this on-request compilation mechanism is that it's a way of producing an executable. So it produces like a machine code representation, but it lays it out in memory in your process, and you can start executing it. And the benefit of that is you don't need to go through like a linker chain. So an alternative, which might be useful for other ways, but not for how we want to use it in the first instance, would be to create an object file and then link that into a library or an executable. So we're able to avoid that, and we get a simpler tool, a simpler chain, and it's kind of useful. So with this IR, you can do this, some benefits of LLVM. So here what I can do, we have some functions. So this is one that takes the IR that we produced, and it's written a machine code file. So if we go and look at I'm using the Unix file command, and it says this is a Mac object bit file. So this is something that I could link into a library or create an executable. And actually, Connor's going to be showing some examples of this. Got to keep a good eye on the time. Right, so you can also do things. Stephen showed this. I can convert this into assembly. So this is assembly that would be suitable for my Mac. And in fact, the object file I produced is just a binary representation of this assembly. Or, this is a good thing about LLVM. It's very cross-platform. So, on one machine, I can produce output that'll run on a different type of machine. And that's often useful, because here I've generated Linux ARM. So Linux ARM is often used in smaller, like Raspberry Pis. Those are useful machines, but they can be slow. So running a big tool chain can be a pain, but I could do all the compilation on a nice, fast, Intel machine, and then target this other machine. So that's what we have there. Now, how are we doing? Another thing that we can do, benefit of LLVM, is we can run optimizations. So we're still tuning some of these things. Maybe machine learning might be a useful way of tuning the optimizations. So here, we've parameterized the optimization sequence that Clang uses. So in Clang, you would do -O3. So here, we're doing Clang optimization level 3, and it runs that. But this is actually this is what Clang is actually doing when you say, and in fact, I think you can give these as arguments to Clang if you want to, but it's quite, and the sequence of what you actually choose to run these, it's not totally trivial. Right, fine. So, parallelism. So it's one of the things that we wanted to, I was always very excited with the compiler, to try to leverage multi-core modern processors. So in a Wolfram engine, there already is a lot of parallelism. There's, this is multi-core, not the parallel toolkit where you fork off kernels, which is also a useful form of parallelism, but this is a sort of lighter weight form of parallelism. So it's quite hard to do this in the Wolfram language itself. The old compiler has some ways of doing this, but it's a little bit awkward. And it was a key goal of the compiler project to be able to do this. So the way that you would, I'm trying not to be, this is kind of schematic. What would be to do this is you would set up some sort of work unit and you'd give it, say, to 4 threads. You'd have them running and then you'd wait till they all completed. There's lots of details and strategies and improvements that you can do with this. But a key requirement for this is to have a compiler that can run with nested functions. So here I've got an outer function, but it has 2 inner functions. So this outer function, so you've got one function where you've got a function here, and this inner function takes a function as an argument, and it applies that to the argument. This is obviously contrived, and the other thing here is this is the inner function. So we pass one function in as the other, and so we can work with this, and we get a little print statement. That's another new thing in new compiler, is to be able to work with strings and do printing and stuff like that. Quite useful just to get some sort of feedback, and this is quite useful. And just you might get a bit more of an idea when you look at the intermediate code. So here's this is the main function. So we have one function here, and this function here has the type signature, first argument itself is a function. So it takes a function that does integer to integer and an integer, and it returns an integer. And then these are the other functions, and then there's the plus function. So since we can work with this, we can pass functions around as first-class objects. That's needed to be able to write, sort of parallel type operations. So now we can utilize this. So a slight defect at the moment of the compiler is the compilation step is a little bit slow, and so I'm starting this up. But basically, what I've written is I've written a parallel map, and it takes a function, and it takes an argument, and the argument is a packed array, and it takes a count. And the count is going to be the number of threads that's used in the operation. So this is calling through after some work, it calls a thread layer that's written in our runtime. And we can invoke this. So here I'm running it. So I'm giving it, a packed array of 10 million elements. I'm saying use 1 thread. But now I'm doing it. I'm saying use 4 threads. So now this particular function, adding 1, I could do that with a listable operation, and that would also be quite fast, and that would also be done in parallel. But because our runtime library supports that, but what our runtime library won't let you do is, for example, if you had something that had a branch in it. So here, I've got some rather silly function. So if the sign of this thing is greater than 0, it does this big blob, otherwise it's this. And there might be more work that we could do to, optimize this. So now I'm going to run this, and so if we use sort of 8 threads, we're getting some nice speed ups, and we could turn on this LLVM optimization and get even faster. But this is quite a good way of leveraging the multi-core nature of the computer. Now, I'm going to have a quick pause, and we're going to look at some other work that Connor
Let's see.
That's on.
Yep.
You just attach that
Clip it.
somewhere.
Clip it. Yeah.
Yeah, there's
Oh, I see. You've got it
just like that.
backwards.
Put it backwards.
Okay.
That, put it in your pocket or something.
Right. Okay. Can everyone hear me? Yep. Okay. I log in. So we're building this compiler, and we're generating executables, native machine code, and there are tools for debugging these programs that already exist, and we'd like to be able to use them. Sorry, what? Ah, yes. Okay. Yeah, I can do that. Okay, and we can make this bigger too. Is that good? Everyone read that? Okay. Just going to run my init code. So we've got, I'm just going to sort of show the changes. So if you're building a program in debug mode, we'll load the program. Sort of Tom showed this, create an inert form of the expression, compile it. Let me make this a bit wider. And we can see that the intermediate representation that we generate has these primitive function debug values added. So these appear in the program wherever a symbol in the source program's value has changed, or maybe it's a function declaration or module declaration, wherever a new variable is introduced or an old variable has had its value changed. And these get translated down into sort of similar primitives in the LLVM IR, which basically do the same thing, except these have, there's more information here that's hidden as properties on these objects, but that's fully exposed in the LLVM IR. So you have these value statements, and they have the variable they refer to, so the actual value where it appears in the IR, and what is the value. And the second argument you can ignore. This third argument is a reference to a metadata node, which actually represents, this was this source variable in the program. If you have in the program that we just compiled, there was an x and a y variable, and that node is visible down here. It's a di local variable. It says, we have this variable n in the source. It appears in a certain place, and it has this name. So when we create something that we might actually want to debug, that's too simple. We're going to do something a bit more complicated. So now we have just a simple program. It counts up, does a sum. Again, a bit contrived, but works to show this off. We'll compile this again. Probably don't need to look at this again, but similar, it's just a more complicated function. It's got some branches in it, so there are multiple basic blocks, but not much different than what I just talked about. So now I'm going to create, so this creates a shared library that we use library link then to load back in. And again, this is, a user using this when we release this would not have to do this, but that's what we got to do now. So I'll get the process ID, and now I'm going to use a program called LLDB, which is sort of LLVM's own debugger, similar to GDB, a bit more modern though. So we'll run this, and I will attach to the kernel process 6.9. And there's this first little thing that we can continue past. And then I will actually run this function that I've just compiled. We can see we hit the breakpoint that appeared, and we can look at the local variables. Oops. So I'm printing the local variables. You can see they appear there. Now this is a bunch of assembly, and I could step through this for a while, but it would get tedious after a while. We haven't even made it to the, oops, to the first, oh, they're optimized out there. Haven't even made it to the first spot, the second iteration of the loop, so this is kind of useless. But that's okay, because if we do this a different way, instead of loading the expr from the notebook, we can load it from a file after turning on the debugger. So this sort of activates part of the kernel and causes it to annotate the actual expression with line information, which we can make use of in our compiler to generate executables that keep that information. So here's the inert form of the expression, or inert form of our source expression. It's the same program from before, just from a file on my desktop. And we can sort of inspect this, and we can see this breakpoint that appears in the third line does indeed, we remember that it appears in the third line, and we can create more LLVM IR from this, go through the steps. We can see each of these statements in the LLVM IR are annotated with a debug tag. So this sort of says this statement in the program, in the compiled program, appeared in this place in the source program. So we can actually look at these, say, okay, we're the condition loop, the value for whatever 0 is, I think that's probably the counter, appeared online, where it is annotated with debug node metadata 17. We can go find that, and it's a location in the source program, line 4, column information, currently not accurate. So now, get to the fun step, actually create, again, as we did before, a shared library, load this function from that library. Should just make sure this is still correct. Yep, obviously. And run this function. And we see here in LLDB, Wolfram language source code that we can step through, inspect the local variables, just like we would in a C program or anything else, exactly the same. And we can actually do that. Check this out. Some initial values, step through, maybe to the end of the loop. We can see that our counter is changed, or our sum is changed. Go up to the next iteration of the loop, same thing. Have to go after the sum, of course. Yeah, now sum has changed. So we can see this is working. Oops, that's not very helpful. Yeah, and we could continue step through this a few times, get to the end of the loop. Again, just updating the values exactly as it would, you might see, and if you're debugging an equivalent C program. Get to the end, finished, step through, and that's our driver program. But we don't need to look at that. So yeah, that's basically it. We've attached to the Wolfram kernel process, and we can look at compiled code in the same way we would compiled C code. So yeah.
This is the steps we're doing, these annotations. That's what Clang does. When you do clang-g, if any of you write C code, it's up and time. Right. So that's a benefit of working with LLVM. Using, we don't have to write that, it comes for free with quite a lot of work from Connor actually to add those annotations, but still that's pretty nice. So now I just want to finally end in the last few minutes, look a little bit at what coding in this new compiler system looks like. So in the old compiler, you just got one function, and that was very limited. But now we have a bit more, we have more flexibility. You can add types and things. You can add more function definitions. We're not in version 1 going to be supporting down values. And in fact, the whole down value mechanism, pattern matching, can benefit from this technology. But we are being focused, trying to get this finished to get a first release, and we're focusing on function compilation. But what you can do is you can add code to a type environment, and you can do some interesting things. So here I'm getting like the default type environment, and I'm going to add a definition to it. So I'm adding a definition of a GCD. There's a story why I was interested in GCDs, but this is if you go and look at Wikipedia, this is the implementation of a GCD. So I've added that, to the type environment. So now I can invoke this from, if I do a compile, using the same type environment, it'll find that definition and it'll use it. So now I'm calling it. These things are all going to get a lot faster, and I can call this. So yep, that's great. Looks like the GCD of 30 and 12, 6 sounds feasible. So more optimizations in this function here. It's making recursive calls, but actually many of them are what's known as tail recursive. So they're just kind of at the end, just before the thing exits. And that would be a quite feasible thing for us to write an optimization pass to detect these recursive calls and then add, all we need to do is add an metadata to that call instruction saying this is tail recursive, and then LLVM will optimize it. So that's kind of a nice thing. Right, here is a faster version of the binary GCD. You don't have to look at this. Wikipedia has a nice description of this. And now I'm going to invoke this. And basically, instead of doing divisions, it's doing bit shifting as a faster way of doing this. GCD normally does quotient remainder type division, and then it sort of switches them around, and what you're left with is the GCD. But this is a faster way of doing this. And this one here avoids recursion, and it gets the same answers. Now, I'm going to recompile both of those. Second time round, it's built up this cache, which need to build in. And I've turned on LLVM optimizations. And now I'm going to invoke this with kind of a bit of a worst case situation. So these are two large numbers, really quite large numbers, that are relatively prime. So it's going to have to do an awful lot of work to figure out, actually they're relatively prime, so the GCD is 1. And I'm comparing the recursive one, the non-recursive one, and the built-in GCD, which actually uses the same algorithm. But this is the built-in GCD, but the one we just wrote is faster. And let me stress, people quite often come along and say, oh, I know, I've written this faster way of doing something. And if you take some more limited domain, of course it's easy to make something that's faster. You might write a function that just knows that these two inputs has, the answer's 1, but this isn't a limited domain. This is taking the same, so that's quite good to write essentially top-level code that beats the sort of built-in thing. Now, another thing we can do, if I can find my mouse, is, now what happens if we want GCD computations, but I don't want it for integer 64. I want it for unsigned integer 16, image processing, very important to have. So, do we have to copy everything, rewrite it, copy and paste? No, we don't. We make one new implementation, but we write it polymorphically. So now the type signature, which was integer 64, we write it as with a type for all, and we say there's type variable. So the argument has to be a set of signed or unsigned integers, and it has these. So one implementation will then go and work in this whole range of ways. So that's kind of useful. Now, I think that's probably, I'm not going to look at. So, I think I'm coming to the end of the talk, running out of time. Maybe I have a few questions. There's a few more talks coming up at the conference. Later this afternoon, Roman's giving a talk on parallelism. That's using some new technology in our private clouds. Seems like a good use of private clouds to, make a parallel computation. Mark has, the other thing with parallel implementations is often you need new algorithms, and Mark has a description of some interesting ways of doing solving ordinary differential equations with parallel techniques. That's something that we're quite interested in trying to code into this. There's a talk on Friday that is kind of the theorem proving and the type theory aspects related to the type system that I was talking about. And then also on Friday, Abdul's giving another talk on the compiler with some other interesting ways of using it and some of the possibilities and advances that we should be having. So, to summarize, I've given an outline of the new Wolfram Compiler. It has lots of possibilities, but the one thing people always ask me is when's it going to be out? So we're working extremely hard to focus down on a version 1, which I think we're getting closer to coming out, hopefully, and maybe not in the next major release. I would hope strongly that there'll be some that we'll be having something. I think that's quite feasible. And it'll have features, similar features to the things I've been showing today. So multi-core parallelism, a wider range of integer and float operations. And we need those in other parts of the system. So like, a lot of these machine learning networks that we've been seeing, some of those, they work on, they need to work not with, double precision floating point numbers, they work with single precision floating point numbers, or that's also useful in image processing. So we want to be able to build libraries and tools and things for people to work like that, and I'd also like them to be able to get top-level Wolfram language code and have it run blindingly fast and benefit from that. So I have some string support, that's quite useful. Much easier ways to extend the system, so calling functions, adding recursion, things like that, and some sort of nice fast execution of things. So I think I'll wrap up for now. I could probably take a couple of questions or something, but yeah, thanks very much. Thank you.